Let us look at the important points of crystal field theory. We know that the 5d orbitals of the isolated gaseous metal atom are degenerate, or they have the same energy. But during the formation of a complex, when the ligands approach the metal ion to form a complex, that is metal and ligand, the d orbitals lose their degeneracy. That is, so far they were having the same energy. That is, when the ligand is approaching it, under the influence of that ligand, the d orbitals lose that property of degeneracy. That is, they will attain different energies. That is, all the d orbitals are not affected the same. You know that they have different orientations and shapes. We have seen that many times, that dxy, dyz, dxz, then dx square minus y square and dz square, they are all oriented in different ways. So their degeneracy is lost with the approach of the ligands. And as a result, the 5d orbitals split into two sets. That is called crystal field splitting, when they lose their degeneracy under the influence of the ligand. Now, the pattern of splitting will depend on the nature of the crystal field. If they are octahedral, we know that they will split into the higher EG set, and at the bottom they form the T2G set. The EG set having higher energy and the T2G set having lowered energy. That is, above the barycenter, they are having positive charge. It is not charge, it is higher energy. That is why we give a positive value to that energy. And the one lower to it is having lowered energy. Then for tetrahedral, the splitting is different. That is, they will be having T2 or T2G set on the top and E at the bottom. That is, 3 triply degenerate orbitals at the top having more energy, and the doubly degenerate E orbitals will be having lesser energy. In octahedral complex, the 5 degenerate orbitals, the d orbitals are degenerate, having same energy. They, on the approaching of the ligand, they get an increased energy here, and then from there, under the influence of those ligands, they split into two levels. The lowered energy is for T2G group, and the higher energy is for the EG group. Now that is associated per orbital. For each orbital, it will be having 0.6. That is the number of electrons in these. If there are any electrons there, we will multiply this factor with the number of electrons while calculating the crystal field stabilizing energy. Here we will multiply the number of electrons with this minus 0.4. So there is a lowered energy, and this dotted line in the center is called the barycenter, and that we take as 0. That is between the two, that is taken as 0, the value of that line, or it is representing the 0 value. The amounts or the quantities above it is positive, and that below it is negative. And this is delta O, that is the energy associated, or the energy gap between the EG and T2G set. Here for tetrahedral complexes, again the degenerate orbitals under the influence of a ligand will get increased energy. They lose their degeneracy here, and then it splits into two sets, E set and T2 set. Here we avoid using G because there is no center of less center of symmetry in the case of these complexes. So we don't use that term G here. So it is T2 and E. T2 set having higher energy and E set having lowered energy. So what we have to remember for crystal field theory is that the degenerate orbitals, that is the orbitals having the same energy, will lose their degeneracy with the approaching of the ligand. That is because the d orbitals, all the d orbitals are not getting affected the same. They are, each one is having different orientation. So that is why they are having different energies. Then the 5 d orbitals split into two sets. That is called crystal field splitting. And the pattern of splitting will depend on the nature of the crystal field. In octahedral, tetrahedral, square planar, etc., they will be different.